Today we're looking at section 9.5, derivatives of vector functions in arc length. So students will analyze the vector function, find the domain, graph, determine continuity, find the derivative, interpret the derivative, and find arc length, all with vector functions. So what is a vector function? A vector value function of a real variable, or simply a vector function, r equals r of t, is a function whose domain is a subset of the set of real numbers and whose range is a set of vectors. What does that really mean? So vectors can show magnitude and direction, and they're kind of like parametric equations if you're a calculus student. If you've studied physics to this point, or you're studying physics now, you might have a more detailed definition of it. But for us in calculus, they're very, very similar to our parametric functions. So for a vector function, r equals r sub t, whose domain is the closed interval, where a is less than or equal to t, which is less than or equal to b. The components of r are two real functions. So you have your x function and your y function, each defined on the interval where t is defined. So r is r of t, which is broken down, and you'll notice we're using angled brackets instead of rounded brackets. X of t, y of t. If no domain is specified for the vector function, it is assumed that the domain consists of all real numbers for which the component functions are defined. So that takes us right to example 1. Find the domain of the vector function r of t equals 2t and plus 2, comma, root t. So if we just want to remind ourselves which piece is which, your x component is going to be 2t plus 2, and your y component is going to be the square root of t. So this goes back to domain and range, just like in algebra. Well, if I look at 2t plus 2, there are no restrictions on that. T can be any real value. So for this set, t can be any real value. You can tell me negative infinity to infinity, whatever you want there. For the y piece, we have the square root of t. And we know that underneath that radical, it needs to remain positive, or at least non-negative. So for this, t must be greater than or equal to 0. It can be equal to 0, but it's got to be greater than or equal to 0. So where those two sets of numbers overlap is where t is greater than or equal to 0. So find the domain of the vector function. We'll say that t must be greater than or equal to 0. You want the most restrictive piece. Example 2, discuss the graph of the vector function cosine t, sine of t, for which t is between 0 and 2 pi. So this is kind of like a parametric equation, but we've thrown in a little bit of trig functions. So let's look at example 2. Discuss the graph of the vector function r of t equals cosine t, sine t, where t is between 0 and 2 pi. So the domain has been given to us, that 0 to 2 pi. This looks a whole lot like a parametric equation, but we have some trig functions thrown in there. So if we look at this a little bit, we can say that x of t is equal to the cosine of t. We can say that y of t is equal to the sine of t. Sometimes it's nice just to break it apart and remind yourself which is the x and which is the y. All right, I see a sine and a cosine. What relationship do we know about these? If we go back to our Pythagorean trig identity, we know that cosine of t squared plus sine of t squared is equal to 1. We're all very familiar with that. So if I replace cosine with the x, I now have x squared plus y squared equals 1. So this first piece is an identity. And the second piece we substituted in. And what are we left with? Well, x squared plus y1 is a circle of radius 1. So discuss the graph of the vector function. All right. So just like with parametric equations, we can start with a little table that might be helpful. So when t is equal to 0, our x component and our y component. Well, your x component is going to be the cosine of 0, which is 1, and your y component is going to be the sine of 0, which is 0. So our first point happens over here at 1, 0. If I go to pi over 2, all right, pi over 2, so cosine of pi over 2 is 0, sine of pi over 2 is 1, so now we're up here at this point. I already know that it's a circle, We know where it starts and we know where it ends. So it's going to be drawn in the counterclockwise direction. So we can say it's a circle. It starts at 1, 0, drawn counterclockwise. All right, there you go. Discuss the graph of the vector function. All right, let's see what's going on in example 3. Graph the curve C traced out by the vector function that's given. So what are we going to do with this? I would recommend, just like with that parametric equation, I would recommend making a table. For this table, I'm actually going to show you 2 ways to do this. For this table, I would start out with my t values. I have my x value and then my y value. It did not give us a domain for t, so that means t is whatever each portion would regularly be restricted by. The first one is 2 plus 3t. T can be anything, so that's all real numbers. And then 3 minus t, that can also be anything, all real numbers. So I'm going to start with a -2, a -1, a 0, 1, and a 2. I don't really know what the answers are going to be, but let's find out. It's tempting to start at just 1, but don't forget that that t can be negative. If you're not dealing with time, if you are dealing with time, you would want to start at 0, but we don't know that it's time, it's just t. It's just another variable in here. So my x coordinates, I've got 2 plus 3t. All right, so I'm going to fill these in. That's a -6 plus 2 is -4, -1, here's a 2, here's a 5, here's an 8. If I made a mistake, I apologize. This is a 3 minus t. So I've got 3 minus a -2. This is 5. This is 4. This is 3. 3 minus 1 is 2. 3 minus 2 is 1. All right. So if we graph these, I'm at -4, 5. That's not on my graph. I'm at -1, 4. I'm at 2, 3. I'm at 5, 2, and I'm at 8, 1. 1, 2, 3. And when I'm looking at these look like a slope of down 1, right 3. So if I connect them, I do have a line. And if we talk about arrows, it looks like this. So we have a vector defined function. The other thing that you could do is to do a little bit of replacement substitution. So if I know that x is equal to 2 plus 3t, and I know that y is equal to 3 minus t, I could solve the second equation for t pretty easily. I'm going to switch the t and the y. So t is equal to 3 minus y. So if I start with my x equation, I've got 2 plus 3 times 3 minus y, 2 plus 9 minus 3y. So x plus 3y equals 11. This is the equation line. It's in standard form where you dealt with those x and y intercepts. I know it's been a while. They would be fractional intercepts. If you wanted it in y equals, which might be easier, you would have -1/3 x plus 11 over 3. So 11 over 3 is what? Just a little bit less than 4. There's our y-intercept, down 1, right 3, down 1, right 3. So there you go. You just want to know what direction it was drawn in. Example 4, find the limit of a vector function, the limit as t approaches pi over 2 of 2 cosine t plus 2 sine of 2t. And I bet if I let you do this on your own, you would know exactly what to do. What would you do with the pi over 2? Well, you would just put it in place of your t values. So the same thing is going to be true here. I just want to make sure that we're using the correct notation, or the book's correct notation. So this would be the limit as t approaches pi over 2 of 2 cosine t. You could even put that in parentheses. And then the limit as t approaches pi over 2 of 2 sine of 2t. All right, so cosine of pi over 2, that's going to be 0. So this is 2 times 0, still in those angled brackets. And this would be 2 sine of 2 times t. So 2 times pi over 2 is sine of pi. Sine of pi is 0. So we have 0, 0. And yes, you can have a vector 0, 0. That is allowed. Example 5. Determine whether the vector function e of t sine of t is continuous at 0. So what are we going to do there? You want to check the conditions for which it has to be continuous. So those two things, remember the continuity criteria we had to have. The function has to exist. That was one thing. And then the second thing was the limit has to exist. And the third thing was the function had to be equal to the limit. And this is all at a point. This is going way, way, way back to Unit 1 when we were talking about limits. So continuity, same thing's going to happen here. You want to check out your function. So we're going to do 0. So I want the vector at 0. So r of 0 is going to be e of 0 sine of 0. So e to the 0 is 1, sine of 0 is 0, so 1, 0. So yes, that vector function exists. Number 2, the limit exists. So we want the limit as t approaches 0 of e to the t sine of t. And we know that the limit and the actual value of the function don't always have to match. A lot of times they do, but they don't have to. So same idea here, put 0 in place of the t. So we have e to the 0, which is 1, and sine of 0, which is 0. Okay, so we have a limit. We're good to go there. Now, we want to make sure that r of t is equal to the limit as t approaches 0 of r of t. That's a better way to write it. And in fact, they are. We said r of 0 was 1, 0. We said the limit was 1, 0. So yes, indeed, they do equal each other. This is continuous. All right. Now, great. We know what vector defined functions are. Let's do some calculus with them. So the derivatives, these are going to be good, I promise. If r of t is equal to x of t, y of t, and if x equals x of t and y equals y of t are both differentiable real functions, then the derivative of the vector is just the derivative of the two components, which is so, so, so nice. If I want this in our other notation, we could say that dr dt is equal to dx dt, comma, dy dt. And that should look pretty familiar with that for us. We did exactly that when we were talking about parametric equations, which is terrific. So find the derivative of each vector function. Yes, it is that straightforward. It is. So r prime of t is going to be 2 cosine t and -3 sine t. Finished. Letter B, r prime of t is going to be e of t and then 1 over t, but I forgot my brackets. There you go. Derivatives, no problem. Derivative rules. If the vector function u equals u of t and v equals v of t are differentiable, and the real function y equals f of t is differentiable, then the following is true. True. Goodness, my words are stuck today. Your sum rule could be your sum indifference rule. This is really the derivative of two things separately, so you can find the derivative of the u term and the v term, no problem. This could also be a minus, by the way, plus or minus rule. Scalar multiple rule. If you're going to multiply by a value in the front, so a vector times a vector, right? What does this look like? This is your product rule. So first derivative of the second plus the second derivative of the first. So this is your product rule. or close to your product rule. And then the chain rule, if you have a function inside of your vector, you would have the derivative of the outside of the same thing and then multiply by the derivative of the inside. So here we go. I think I've got a few more examples for you. Yes, we do, and that'll be it. Find the derivative of r3t squared for the vector function r of t equals e to the 2t sine of t. So what are we going to do here? So if I'm looking for the derivative, r prime of 3t squared is going to be r prime of t times the derivative of t on the end, which would be d dx of this 3t squared. And in fact, d dt. Let's make this r prime of 3t squared. Let's put the actual value in there. d dt. So d dt of the 3t squared, we've got the whole thing there. All right, so the derivative, start with that. The derivative of e to the 2t is going to be 2e to the 2t. That's a chain rule. The derivative of sine of t is going to be cosine of t. I'm going to come back to those in a second. And then on the end, we need the derivative of 3t squared, which is 6t. So I need to make two adjustments, and that's to the t values right here and right here. They're not actually t, they're 3t squared. So that's how I need to rewrite it. So this is going to be 3t squared. And this t over here is going to be 3t squared. Okay, that looks better. So let's keep going. This is going to be 2e to the 6t squared. And this is going to be cosine of 3t squared. Now, what do we do with the 6t on the outside? We'll multiply it through. So this becomes, and I apologize, I'm out of space here. 2 times 6 is going to be 12t. And then I'll have the e 6 to the t squared, which is great. And then the second one is a 6t in the front, cosine of 3t squared. And I think, let me just double check. I think that's all we have to do. Great job. Example 8, find r with 2 primes of t for the vector function. Well, we know what that means. If I have 2 primes, that means find the second derivative. So how do you get the second derivative? Got to have the first derivative. So r prime of t is going to be e to the t. The derivative of negative cosine is going to be positive sine. Second derivative, keep going. The derivative of e to the t is e to the t. The derivative of sine is cosine of t. And I think, my friends, that's all we have for example 8. That's it. Easy peasy. Example 9, find the tangent vector to the curve traced out by cosine of t sine of t at t equals pi over 4. So even without a whole lot of instructions here, I bet you can probably figure out what we need to do. So a tangent vector, we need a derivative, because that's what we need with our slope, right? So r prime of t is equal to the derivative of cosine is negative sine of t. The derivative of sine is cosine of t. Okay, where are we evaluating this? We are going to evaluate this at pi over 4. So r prime of pi over 4 is negative sine of pi over 4 cosine of pi over 4. So negative sine of pi over 4 is in your first quadrant. Sine is root 2 over 2, but we're making it negative. Cosine is also root 2 over 2, but that will remain positive. So that, my friends, is your tangent vector. You don't have to do anything else with it. That's perfect. Okay, last thing I have for you. Arc length, one more way to do arc length. We had arc length in regular function notation. We had it in parametric notation. Believe we had it in polar notation, and here we are in vector notation. So if a smooth curve C is traced out by the vector function R and T is between A and B, the arc length C from T to A is the following. Your arc length will be from A to B, that's derivative of R dt. Let's add a little bit more to this. I'm not loving the way that they wrote this out. So you're probably wondering, what are these like double absolute value things? They have a name. I just can't think of it right now. This is actually equal to the square root of dx dt squared and dy dt squared. So that's the piece that looks very, very much like that parametric equation arc length that we had. So if you want to write this out the long way without that symbol in there, you could tell me that it's the integral from A to B, dx dt squared plus dy dt squared. And here's a dt at the end. All right, good. So example 10, find the arc length of the cycloid, and the equation is given from t equals 0 to t equals 2 pi. Well, it gave us the boundaries, which was really, really nice. I'd say let's find the derivative of this thing. So I'm going to distribute those threes. You don't have to, but I think that it will make our derivative solving a little bit easier, especially as we get at the end of the course here. Maybe we're forgetting some of those rules. So 3t minus 3 sine of t and 3 minus 3 cosine of t. So r prime of t, the derivative of the first piece is going to be 3 minus 3 cosine t. Nice. And the derivative of the second piece is going to be, the derivative of 3 is 0. The derivative of negative 3 cosine will be positive 3 sine of t. All right, so what do we have to do with those two pieces? They need to go inside of our formula. So we know that arc length is going to be from A to B. Well, actually, we know A and B are. A is 0, B is 2 pi. Here is your square root of this whole thing. So we need to square the x piece. So this is 3 minus 3 cosine of t, that quantity is squared, plus your y piece, which is 3 sine of t, this quantity squared dt. At this point, if it's a calculator allowed question, you could definitely do that. You would just want to make sure you watch your parentheses and your exponents. If I multiply this out, I've got 9 minus 6 cosine t plus, nope, not 6, 12, goodness. If I multiply this out, I've got 9 minus 12 cosine t plus 9 cosine squared of t plus 9 sine squared of t. All of this is inside of the radical. And sometimes they set these up for good things to happen, and it looks like that's happening here. Because what's cosine squared plus sine squared? You would tell me that's 1. I could factor out the 9 first. So we have a 9 and a 9, which would be 18. So 18 minus 12 cosine t inside of this radical between 0 and 2 pi. I just found an error that I made when I multiplied that out. This would actually be an 18 over here. Okay, so I wind up with 9 cosine squared plus 9 sine squared. I could pull out that 9 and there's a 1, so 9 plus 9 is 18. Minus 18 cosine of t. This is still inside the radical between 0 and 2 pi. Now, you could take out that 18, pull all the way to the front, so you have the square root of 18 in the front, and then you'd have the radical, and then inside of that 1 minus cosine of t. So you can't integrate that by hand. It's not use substitution. You would need a sign in that problem, but there is a half angle trig identity out there that you could use. You could look it up if you really, really wanted to. Your final answer is going to be 24. And let me just jot down that inequality for anybody who's interested. Sine of 1/2 is equal to the square root of 1 minus cosine t over 2. You can do a little bit of manipulating there with the 2 and replace that in the identity to integrate. But regardless, your answer is 24. Good luck with those. Let me know if you have any questions.